start recording and
Okay. It needs to still be switched on? Oh, okay. All right. But here you go.
if he speaks close to you, they'll be able to hear.
All right. Sounds good.
Very good. Thank you for attending this PhD seminar. The last one closes the door. And most of you up here, most of you know Rick Lumpkin. He obtained in '98 his PhD at the University of Hawaii. Then he did a postdoc in Premier and worked as a research faculty position at FSU. And he joined us here at CIMAS in 2002. And he's been a PhD federal scientist since 2004, 2 years later, where he became the lead PI for the Pirata Northeast Extension Project and the Global Drifter program. And has a lot of emphasis on the tropical Atlantic, tropical ocean dynamics, which Rick already has some experience in his work in Hawaii. He has been my deputy since 2015, and it's a pleasure to work with him. And in 2018, he was invited to be the editor of the BAMS, Bulletin of the American Meteorological Society, Oceans chapter, that in the state of the climate. That is one of the 7 chapters of this special issue that is we have every year. And several of us are authors or co-authors, have been for the last year. So it's a pleasure to introduce Rick Lumpkin, that he will tell us, give us a summary version of all the important results that tell us about the state of the ocean in 2018. Thank you,
right.
Rick.
Thanks, Gustavo. So let me just dive right in, since he's covered the first slide. So let me first talk about what the State of the Climate Report is. It's an international peer-reviewed publication. It's released every summer, and it's considered the authoritative annual summary of the global climate, published as a supplement to BAMS. You can see last year's report I'm holding here. You can kind of get an idea of the thickness of it. So it's a pretty substantial, pretty hefty publication that's put out every year. It's compiled by the Center for Weather and Climate at NCEI, based on contributions from scientists from around the world, but there's an very large representation of NOAA in the list of authors. The goal is to provide a detailed update on climate indicators, weather events, and other data collected around the world. Here are the 7 chapters of the State of the Climate Report. So you can see there's a very brief introduction generally that kind of gives the overview. It'll, for example, tell you if there is a large El Nino or La Nina, kind of what that dominant interannual mode was, and then it moves straight into a global climate chapter, and then the chapter Global Oceans that I was the editor of for this year's report. Then tropics, the Arctic, Antarctica, and regional climates is the final chapter. So this 2018 report is the 29th one that's been issued, so that they've been coming out since 1996. The lead editors this year, as last year, was Jessica Blunden and Deke Arndt of NESDIS, NOAA, NESDIS, and CEI. And one of the unusual things that happened, of course, this year was the shutdown in January. That normally what's happening is we're getting our data put together through December. Everything is kind of compiled, and we start working by the second, third week of January. This time around, all of that was delayed, so a lot of us came back after the shutdown ended and still had to wait a significant amount of time for the data through the end of 2018 to be compiled, especially, by a number of these are dependent on the NOAA sources. So that's pushed everything back about a month in our deadlines, and we're trying to catch up, but we'll see if we can stick to the same schedule. basically, right now we should be getting the external reviews back if we were in a normal time frame. Instead, the chapters are still out for external review. So we're waiting to get those reviews back and hoping to be able to move closer to being a kind of a similar timeline to previous years.
This is a minor issue, but 29th issue since 1996, it means that it was more than annual.
It's an interesting point. I've actually copied word for word what they said, so maybe I've copied a typo. I didn't count it out, but either way, it's a lot. I had no idea it went back that far, to tell you the truth. But yeah, so but there have been quite a few of these issued apparently, and perhaps there was more than annual earlier on, and they realized that's overkill. So the sections are listed here. There's an overview. Then we go into SST. Each year there are two sidebars that focus on particular interests for that year. So for this year, Gustavo was my editor for the sidebars and helped, and he identified the authors for these two sidebars. One on the Sargassum Blooms, and the next one you see further down on the red tide bloom. Then there's a section on heat content, salinity, air-sea fluxes, sea level, surface currents, phytoplankton, and the ocean carbon cycle. A lot of authors. This is for this one chapter. So you can see here's the first 30 of them listed here, and the rest of them down to author number 57. So the lead authors of each section are coordinating with all of their co-authors and all kind of reporting to me as the lead editor of this to keep everything kind of moving and on track, and come back with the internal review, which we've gone through that process, get everything revised, compiled, and submitted for external review. And that's kind of what we've gotten through at this point. So it's a pretty huge project with lots and lots of people all around the world. You can just, as you scan through that list, see, first of all, you notice a lot of NOAA authors, as I mentioned before, but not all, and you also see authors from other places around the world. So we really do look for global input on this report.
Did you see the question that somebody asked?
I didn't.
We asked to repeat the question. Whenever someone asks a question, if you can repeat in the microphone.
So whenever there's a question asked, the question was for me to repeat it in the microphone. So I'll try to remember that later in the talk when I get some questions, since the microphone's not picking up the audience. All right, so let's start off with the overview that I wrote. I wanted to emphasize the importance of the oceans, and of course this has been done in many years, but I wanted to put a little bit of my spin on it, and this is what I wrote to try to say why we should care about the oceans when we're looking at the climate. The oceans are the memory of the climate system at timescales from subseasonal to millennial. They absorb vast amounts of heat, carbon dioxide, and other properties from the atmosphere, store them throughout the water column, transport them via a network of interconnected surface and subsurface currents, and ultimately return them to the atmosphere or sequester them in sediments. Focusing on 2018, this chapter describes the evolution of sea surface temperature, ocean heat content, salinity, fluxes, sea level, currents, phytoplankton, and carbon. So that's the big lead-in. That's what I want to do to get people hooked and start reading about this. And thanks to some wordsmithing from folk here who read and gave me some comments and suggestions. I didn't think about the sediments, for example, until I got a nice comment from Greg Foltz. All right, the highlights I will give you now before I start going into the individual sections. Globally average sea level reached the record high in 2018 for the 7th year in a row. Globally average SST has cooled slightly over the last 2 years since the record El Nino SST high in 2016, but it's still far above a climatological mean, and we're obviously looking at interannual variability superimposed on a long-term increasing trend. In the Atlantic Ocean, SST patterns show the characteristic tripole fingerprint that we expect of an MOC slowdown. The upper 600 meters of the Atlantic has steadily become saltier. Chlorophyll A concentrations were suppressed by 10 to 30% in warm SST regions. There's a new estimate of ocean uptake of anthropogenic CO2 due to riverine input, which it basically increases the ocean uptake by 20%. And the sidebars are going to, as I mentioned, handle two particular bloom events that cause significant economic damage, both in the Caribbean and around Florida. So, the sea surface temperatures section, you can see the list of authors here, Huang, Kennedy, Xu, and Zhang. We start off looking at the, oh, and by the way, I'm not going to get into the methodologies. Every single section has a very in-depth description of the methodologies used to produce these plots. I leave that to you. If you want to know the details, I'm happy to provide that information, but I'm not going to get into all of the data sets that go into these plots you're going to see here. Otherwise, I'd be spending 3/4 of the talk doing that. So let's look at sea surface temperature. Here we see in the top the 2018 anomalies with respect to climatology, in this case 81 to 2000. That climatological period is going to differ from one data set to another, or from one variable to another because of what we can do and what we can measure. So what you basically see is a warmer world, just about everywhere, with some exceptions. The cold tongue in the eastern equatorial Pacific is one notable exception. You see an area in the Erminger Labrador Sea that's colder, and you see a region in the far southeast Pacific where data is relatively sparse, but it's showing colder temperatures as well. Everywhere else warmer. And that tripole pattern is consistent with a Caesar et al. Study that we had a PhD discussion about. You see the cold south of Greenland, and then warm and then cold pattern. Especially that warm and cold part are exactly what we expect to see if the meridional overturning circulation in the Atlantic is slowing down. We expect to see that the reduction of heat to the far north causes a relative cooling there, and we expect that as the deep western boundary current weakens, the Gulf Stream shifts to the north as a consequence of potential vorticity conservation, creating a warm anomaly to the north and a cold anomaly to the south. So that tripole pattern is what we would expect for an MOC slowdown. When we look at the 2018 minus 2017 map in the bottom, we see a general cooling. As I mentioned, there's been a cooling since 2016, the record high, and that is what that particular pattern looks like, with some regions of warming, including the far North Pacific. Here's the seasonal evolution. This is, top left is December, January, February. Top right, March, April, May. Bottom left, June, July, August, and then September, October, November on the bottom right. And so we started the year in a La Nina state. You can see that from the equatorial SST anomalies. That just steadily weakened through the year, and then warm anomalies began developing in the far western Pacific of a nascent development of an El Nino. But by the end of the year, that was not fully formed and was still called a theoretical or potential El Nino in this chapter. Here is your long-term time series picture. The top two are both global ocean. What you're seeing in the top right is for the entire instrumental time period from 1880 to the present, and top left is the same time series but from 1950 to the present. So you can see kind of the zoom in. And that same time period is then reproduced for different basins in the panels below, and you can read to see which basin you're looking at. So you see that, as I mentioned before, can you please hit mute? One moment, technical difficulties. Okay. I knew I shouldn't have used my wireless guitar. All right, as I mentioned before, 2016 was a record high, but you can see clearly we're looking at interannual variability superimposed on a trend, and that trend is something like 0.1 degrees per decade over the time period 1950 to 2018. In 2018, the anomaly global is 0.33 degrees C, down from the 0.44 degrees C record of 2016. When you look at individual basins, you find that from 1950 to the 2018, the warming is greatest in the tropical Indian Ocean, smallest in the North Pacific. But as you can see, particularly in the Pacific and Atlantic basins, it's very sensitive. This difference is very sensitive to what your starting point is because of that interannual and decadal variability superimposed on this longer-term increase in temperature.
You can minimize this.
Okay, thanks. All right, so let's talk about sidebar one then. This is looking at the Sargassum Blooms in the tropical Atlantic. Hu and Wang are the authors of this section. Using satellites, the area covered by Sargassum can be estimated. You see in the inset, first of all, a time series of sargassum coverage derived this way, and you can see this very rapid increase in recent years. And then the shading in this larger map is the trend. And you can see the percentage colors there in the color bar at the bottom. So what you see is this very significant increase over the time period. And the section itself describes the inundation of numerous Caribbean beaches since 2011. It says that, in general, every summer the coverage peaks, but it's been incredibly large in these recent years. And 2018 was a new record high for sargassum coverage. The authors then look at what has changed. Why are we seeing this dramatic increase in sargassum? So they note rising sea surface temperatures, enhanced nutrient inputs from rivers, dust, and upwelling, and recent climate change and ocean current variations may have in some way combined to create favorable conditions. And that's effectively the extent of this speculation that they have in their section. Ocean heat content was led by Greg Johnson with co-authors Lyman, Boyer, Cheng, Dominguez, Gilson, Ishii, Killick, Monsellison, Perky, and Wiffles. So here we see the 0 to 700 meter ocean heat content anomaly. It's with respect to 93 to 2018. You see generally reds in that map on the top. That's the 2018 anomaly with respect to the overall time period. There's a decrease, though, across the band in the Pacific and an increase south of that kind of zonal band. This corresponds to an increase in the north equatorial countercurrent of the Pacific that you'll also see in the ocean currents section. The authors note that this is reminiscent of the tilting mode involved in the recharge of equatorial Pacific warm water prior to an El Nino. The large cold area south of Greenland has persisted since 2014. This is also seen in sea surface temperature anomalies. Warm conditions off the east coast of the US since 2009. So it's not just seen in sea surface temperature, it's seen in ocean heat content. You see the 2018 minus 2017 map really emphasizes that change in the tropical Pacific Ocean. So that's not so much a long-term trend as a recent change in 2018 with respect to 2017 and earlier years. Here's a time series globally averaged of the ocean heat content anomaly versus depth vertically and versus time horizontally. The curves to the right give you what the trend is. First of all, just the raw trend in red, and then if you basically kind of correlate this with a El Nino and remove that, you get the blue curve. So in 2018, the entire water column is warmer than the average. You can see the general shift from blues to reds. The 0 to 100 decibar level cooled from 2017 to 2018, consistent with sea surface temperature, but the deeper waters are steadily getting warmer still. You can see from 100 to 1,000 waters are warmer with a core of warmth at about 160 decibars. There's also a local maximum warming at 600 decibars. The authors noted that this redistribution may be partly due to the Earth system adjusting from the 2016 to 2017 El Nino. By combining the Argo data with ship data, we can go back further in time. You can see once we don't have the Argo data, the curves from the different products become less correlated, but they all show the general increase of ocean heat content from the early 90s to the present. The overall increase then, if you fit it over this time period, is something from 0.36 to 0.42 watts per square meter energy input into the ocean to be consistent with this kind of increase in heat content. And 5 out of the 6 estimates, you see this at different estimates here, 5 out of the 6 put 2018 as the highest year on record for 0 to 700 meter ocean heat content anomaly. From 700 meters to 2,000 meters, a number of the products show a slight decrease from 2017. And only 2 of the 6 records put 2018 as the highest year on record. But you still see this overall trend of anywhere from 0.14 to 0.32 watts per square meter increase of the deeper ocean's heat content. Salinity, Johnson, Reagan, Lyman, Boyer, Schmidt, and Laccarnini. Here you're looking at sea surface salinity anomalies with respect to 2005 to 2018. And they show that the subpolar regions are becoming fresher while the subtropics are becoming saltier. And they note that we basically expect to see this in a warming world, the hydrological cycle accelerating. So the drier places becoming drier, wetter places becoming wetter. And that pattern seems to be reflected in sea surface salinity anomalies here. We see very fresh anomalies in the Pacific intertropical convergence zone and subpolar convergence zones, and also near the mouth of the Amazon and Orinoco rivers. When we look at the difference between 2017 to 2018, so this 1 year change in the middle, they really closely track the precipitation minus evaporation anomalies that I'll show you when we get to the fluxes section. For example, the very dramatic signal you see of the increasing salinity around the maritime continent here. You'll see this again when I show you the P minus E anomalies. So that explains patterns like that have changed very dramatically just in the course of the last year. And then shaded at the bottom, it's not showing up well on the screen here, are the trends for the Argo period, 05 to 18. Again, just showing salty regions becoming saltier and fresh regions becoming fresher. Here is a change in salt anomalies versus depth and versus time for the 3 different basins, Atlantic at the top, Pacific in the middle, and Indian Ocean at the bottom. The Atlantic is generally becoming saltier every year. 2018, in fact, set a record as the first year for which all 0 to 1500 meter salinity anomalies were saltier than the long-term trend. So another record set there. In the Pacific, we have fresh anomalies in the upper 100 meters that are generally becoming fresher. Salty anomalies at 100 to 250 meters, and then kind of another region of fresh anomalies you see beneath that. And the upper 100 meters are becoming fresher over time, and you can kind of see that in the trend. Just you can eyeball it, or you can see it in the trend plot to the right of the contour plot. The Indian Ocean is a more complicated looking picture. You can see that from 2016 to early 2018, there's generally salty anomalies throughout the water column, with some near surface freshening in mid 2018, which you really can't see easily on this particular map, but you can see it in the geographical map. Air sea fluxes. Lisan Yu is the lead author with Jen, Stackhouse, Wilbur, Cato, Loeb, and Weller. Here you see the net air-sea heat flux. You see a general anomalous ocean heat gain. This is an anomaly with respect to climatology. You see a heat gain in the equatorial and southern Pacific. Those are the red areas. So that's the ocean getting heat from the atmosphere. And then heat loss in the subtropical North Pacific, North Atlantic, and the southern high latitudes. And these, as you'll see when I show you the wind anomalies, are related to those wind anomalies through turbulent fluxes. When you look at the 2018 minus 2017 patterns, those are very strongly related to the turbulent fluxes. They have individual plots of each one of these terms in the report, which I did not repeat for this presentation. Here's the P minus E anomaly for 2018 minus climatology. You see a net freshwater input increased in the northern tropical Pacific and tropical Indian Ocean, but then decreased in the south tropical Pacific and mid-latitudes in both hemispheres. And when you do the 2018 minus 2017, there's that anomaly I was talking about around the maritime continent. You can see in 2018, there's anomalously very, very dry conditions over that particular region, which is then related to those very salty anomalies that we saw in the 2018 map there. So we're seeing, the evidence of this year-to-year changes as well as these longer-term trends. Here are the wind anomalies for 2018. At the top left is the climatology, and top right is 2018 minus 2017. The 2018 anomaly showed us that the trades are weakened north of the equator and strengthened south of the equator in the Pacific. Westerlies increased significantly in the mid-latitude North Pacific and Atlantic and along the Antarctic circumpolar current. The strengthening of surface winds associated with the NAO, with a positive NAO, is very clear when you look at the 2018 minus 2017 maps. You see that in the North Atlantic. There's also anomalous patterns in the North Pacific that were related to the reemergence of the warm blob in that area. When we look at long-term trends of the fluxes, it's a kind of an interesting picture of ups and downs, dominated, especially with net heat flux. It looks really dominated. Remember, this is an anomaly with respect to this overall time period. There's basically a maximum in 2016 associated with El Nino, very sharp drop in 2017, increase in 2018. but we don't see much of a longer term trend than that over this time period. We can go further back with P-E and with wind stress, and what those time series seem to show is a regime shift around 1999, where before that there was a steady decrease globally in P-E and an increase in wind stress, which then seemed to flatten out after that. Kind of an interesting, odd-looking pattern that I don't know if we understand. Sea level, led by Phil Thompson with Woodlansky, Llewellyn, Sweet, Chambers, Hamilton, Jevrejeva, Mara, Merrifield, Mitchum, and Niram. Globally averaged, you see here, global mean in black, ocean mass in purple, estimated, the steric part in red, the ocean mass plus steric sea level in blue, and then the inferred in light blue. Another record setter, 2018 highest annual average in the satellite altimetry period at 81 millimeters above the 1993 average. 7th year in a row that a new record has been set. And out of the last 25 years, 23 of them had higher sea level than the year before, globally averaged. It's just a steady increase, 3 millimeters per year, plus or minus 0.4. Basically. And when they look at those individual, the steric versus mass input, it's the mass input that's 2/3 of the trend that they're seeing over this time period. The acceleration is hard to derive from the raw signal, but if you correlate the Pinatubo cooling effects and the ENSO effects and subtract that to get the longer term trend, you also can derive then a significant acceleration of sea level, and that acceleration is 0.084 millimeters per year per year. Here's the spatial pattern of sea level rise, 2018 with respect to climatology, and 2018 with respect to 2017. You can see 2018 sea level is generally higher everywhere, except for that region in the Labrador-Irminger Seas of cooling, and a zonal band in the tropics, tropical northwestern Pacific. This is related again possibly to that acceleration of the north equatorial countercurrent. And we see particularly that was a very large change from 2017 to 2018 when we look at that difference map on the right, and you see this very big shift in sea level just in that 1 year. So that is related likely to the erosion of the La Nina and the development of kind of a precursor to El Nino state. The second sidebar of the oceans chapter is about the Florida red tide bloom. It was led by Chris Kelbel with Karnauskas, Hubbard, Goney, and Streeter as co-authors. We all here in South Florida have read a lot of articles about this. This sidebar summarized a lot of the economic damages caused by the blooms around the state. You can see places where the red tide was sampled in the map on the left, and then the time series in different locations showing these very large blooms when you look at the number of cells per liter of the dinoflagellates such as Carina brevis. The sidebar notes that this is something that's happened for as long as we've had historical records, but it's very, very long-lasting blooms is kind of what's anomalous in these recent blooms, and the intensity of them that have resulted in extensive wildlife mortalities and strandings, numerous reports of respiratory irritation of people, harvest closures for shellfish, and reduced tourism, which has been documented in local papers and such as well. From late 2017 to early 2019, the red tides persisted along the southwest coast, and fisheries landings decreased significantly, and a table in this chapter documents that quite clearly. So that red tide bloom initiated off of southwest Florida and intensified after passage of Tropical Storm Gordon in September 2018. Bloom concentrations were then detected off of the Panhandle and off of Florida's east coasts. And one of the things that the chapter notes is that the currents during this time period supported the transport of that bloom to the east coast. You can see it was kind of a shortcut pathway taking the loop current around through the Florida current to the east coast. So it's likely that the bloom was entrained in that and pulled over to our side of the state. Surface currents, Rick Lumpkin with Goney and Dohan as co-authors. This year was not a particularly dramatic year compared to some previous years. 2016 was an exciting year to write this chapter. The main signal we're looking here at anomalous zonal currents in 2018 with respect to climatology, which is over the altimeter time period, and then 2018 minus 2017. And in both cases, what really stands out is the development of an accelerated north equatorial countercurrent, which is 10 to 15 centimeters per second faster than in climatology, and also extending anomalously northward of where the NECC is typically located in the Pacific Ocean. And as you've seen in earlier plots, this is related to this anomalous pattern of ocean heat content. It's also associated with the anomalous wind stresses that we saw in the flux chapter. When we look at surface current anomalies and how their relationship to sea surface temperature anomalies, it's pretty clear that the surface current anomalies lead temperature anomalies. And we can see that in this time series. This is looking at the time series and spatial map of the first EOF of surface current variations and SST variations, 93 to the present. Over this time period, the correlation between those two anomalies is R equals 0.65, with surface currents leading sea surface temperature by 76 days. So generally, if you want to know what the sea surface temperature is going to do in the Eastern Pacific for El Nino kind of variations, you'll see the current anomalies appear first, and then they will affect those warm temperature anomalies into the region. Global ocean phytoplankton, led by Brian France with Satinic, Caracollu, Seagull, and Westbury. So now we get way out of what I, as a physical oceanographer, have a lot of experience in, but I definitely learned some things from reading this chapter. For example, marine phytoplankton contribute about half of the net primary productivity on the planet Earth. There are two different ways of looking at what's happening with phytoplankton. One is the chlorophyll A concentration at the top, and in the middle, you're looking at the phytoplankton carbon biomass anomaly. Now, you can have more biomass or equal biomass with less or more phytoplankton, or excuse me, chlorophyll, because of the health of the phytoplankton. So these two different things kind of give you a good picture of what's happening with phytoplankton in the ocean. We see from the top map that concentrations are reduced by 10 to 30% compared to climatology in the regions of high SST over the same time period. And because it's not the exact same time period as the SST chapter, we see the SST anomaly with very similar looking patterns at the bottom here. When we look at phytoplankton carbon biomass anomalies, we see that tropical Pacific concentrations are a similar but weaker pattern than the chlorophyll concentrations. Negative anomalies in the east, but neutral to positive anomalies in the west. And they're generally more homogeneous across the Atlantic and Pacific than the chlorophyll anomalies. You see a more spatially patchy distributions of those anomalies in chlorophyll. They noted that positive SSTs coincide with shallower surface mixed layer depths. Okay, so that's one of the factors going on here. You basically trap the phytoplankton in shallower water. It's exposed to more prolonged sunlight, and phytoplankton responds to that by decreasing the amount of chlorophyll in the cells. So that's one reason you would see this correlation. But another thing that could be happening is that the shallower mixed layer depths are also more stratified, so that less nutrients can get into the mixed layer for the phytoplankton to be able to grow. So you can have an inverse relationship between chlorophyll A and SST from either of these two things. But they have opposite implications on phytoplankton net primary productivity, according to this Barenfield et al. 2015. I wanted to try to understand that a little bit better since I didn't understand what that meant. And what Barenfield et al. Kind of concludes is that contemporary relationships between chlorophyll changes and ocean warming are not indicative of proportional changes in productivity, as light-driven decreases in chlorophyll can be associated with constant or even increased photosynthesis. Extension of these results to future change requires further evaluation of how the multifaceted stressors of a warmer, higher CO2 world will impact plankton communities. I think the summary of this is that we have a lot to learn, but at least we're making the observations that we'll need to put that basic research in and understand what's happening. Global Ocean Carbon Cycle was lead author Dick Feely with co-authors Rick Wanenkoff, Carter, Landschutzer, Sutton, Kuska, and Ternanis. They started off by noting that the atmospheric concentrations of CO2 are higher than they've been for the last 800,000 years. So we are performing that grand experiment on our planet that we're all well aware of. Of the 11 petagrams of carbon per year of anthropogenic carbon released during the period 2008 to 2017, about 2.4 have accumulated in the ocean. That's 22% of that anthropogenic carbon. In 2018, this Resplandi et al. Paper was published, which increased upward the amount of anthropogenic carbon going into the ocean from rivers, from 0.45 to 0.78 petagrams carbon per year. So that's a fairly significant increase in the estimate of how much net anthropogenic carbon dioxide is going into the atmosphere. You can see the monthly air sea flux in blue, the annually averaged in red, and then that offset is when you include that riverine input. So you can see that basically the fluxes, anthropogenic fluxes of carbon from 82 to 2018 show that there was a kind of a decreasing ocean sink in the first part of the record. You get to that peak, but then a very strong increase from 2001 onward that continued in 2018. When you look at the distribution of the air sea CO2 flux in 2018, you see this top plot here. This is moles of carbon per square meter per year. The characteristic pattern is basically you have the release of carbon dioxide from the ocean to the atmosphere at low latitudes in warm waters in coastal upwelling regions, and then you have these very large sinks in the cooler waters at higher latitudes. There's also a relationship with upwelling and with local productivity, though. It's not simply a function of the temperatures, as you'll see in the next slide. But when you look at the bottom, we see the anomalies relative to the 96 to 2016 average, showing where there's increasing ocean CO2 uptake with time. And these are related to things such as the ENSO anomalies in the eastern equatorial Pacific. And then when we look at higher latitudes, these are associated with anomalously warm 2018 SSTs. So remember, it's an anomalously cold SST in the equatorial Pacific here, but anomalously warm SSTs. And they both have the same sign of air sea CO2 flux anomalies here. That is because there is this temperature relationship between how much carbon dioxide the water can hold as temperature, but also in the equatorial Pacific, you have variations of how much water is upwelling to the surface related to the El Nino. So when you look at the sea surface temperature anomalies versus time at the top, this is averaged from 5 north to 10 south. And then you look at PCO2 in the middle, you see this general increase in PCO2, but you also see very clearly that when there's a very strong El Nino event, that basically the upwelling is ceased, is terminated, and the atmosphere and the ocean are effectively in equilibrium, and the PCO2 becomes very small in those particular years. And you can see that very clearly if you look at, kind of line up with your eyes, the middle plot and the bottom plot. And the inverse relationship is holding for the La Niñas when you have very strong increase of cold water brought up to the surface that's very much out of equilibrium with the atmosphere. Here is the deseasoned monthly means of PCO2 at Woods Hole, the Hawaiian Ocean Time Series in blue, and you can see this steady increase. Also, in that the blue dot and the map in the inset is where HOTS is located. The red dot is the Stratus time series. The red dots time series you see in the large plot, and then atmospheric CO2 at Mauna Loa Observatory in black. So you can see these all show a very, very similar trend, increase of about 2 microatmospheres per year. And the final figure of the carbon section was this very cool plot of the amount of the change of anthropogenic carbon in micromoles per kilogram over the time period, let's see, 94 to 2007. It is basically derived from the Woese, Clivar, and Ghost Ship observations, plus a data synthesis and quality controlled product that Olson et al. Published in 2016. And this quantification was published in Grouper et al. 2019. So you can see this really cool spatial distribution, which obviously maps out, for those of you familiar with the, well, first let me step back and describe what you're seeing. So you're seeing the Pacific sweeping off to the right, the Antarctica and the Southern Ocean in the middle, the Atlantic coming towards you, and going off away from you to the left is the Indian Ocean. So you see, anyone who knows and is familiar with the global overturning circulation sees these places where the ocean is sinking, the water is becoming dense and sinking and making the lower limbs show this enhanced increase in anthropogenic carbon content, and places where there's general kind of upwelling and rising of waters, you see, at least for now, a decrease in anthropogenic carbon while the system is very much out of equilibrium. And this system takes, tens of thousands of years to have an equilibrium. So it's a really fascinating map of how anthropogenic carbon is acting as a tracer for the global overturning circulation patterns. And that's all I have from this. It's I think, a good place to wrap up. And thank you for your attention, and to take any questions that you may have. Yes, and if you have any questions online, if you're in the GoToMeeting, please type them. We have you muted, so please type them, and we'll see them in the chat window. Guys, it's an interesting year. Usually it's a bit easier to write this up when we've had a really dramatic climate signal or climate fluctuation like in an El Nino year, but I think that a year like 2018 gave us a chance to focus more on longer term trends, which was nice to turn to, because it's a little too easy to get obsessed with the very dramatic year-to-year change that happens when we have a strong El Nino or La Nina event. Rick, I'd like to ask you, if you could, to speak up on the carbon chapter. I'm obviously no expert on that, and I wonder if there's anything you'd like to add about that input.
No, you did better than I would have done. I learned a bit. No, I do think sort of the things that you touched upon is which we are really sort of trying to wrap our head around in carbon cycle work is one is the plot where we see sort of this minimum uptake in 2005, and then it accelerated was the first slide that you showed, this one right here. Why in the early 2000s we see this minimum uptake and the rapid acceleration after that. This is pretty firmly established from several different lines of evidence, but we don't have a full grasp of why there is these decadal scale variations in uptake. Our conventional wisdom is that what you showed, that the ocean takes up the excess carbon in a very regular fashion. So that is something that is an ongoing research topic, but we have confirmed that this is indeed, it was first shown in models. Now we have it in observations that this is we believe it's real, but we don't fully understand the mechanism behind that. And then the second sort of highlight is, which you did as well, showed as well, is these decadal snapshots that we believe are sort of hold the absolute truth. There's a lot of uncertainty in the flux measurements, and so we determined the uptake really from these decadal snapshots from the hydrographic surveys, and so the Gerber et al. is really sort of a highlight of the carbon cycle, ocean carbon cycle for this year. But sort of to continue, first of all, I think all of us owe you a big thanks for taking on being the editor, and you've done it conscientiously, and we really appreciate that. So
thank you.
We also hope that you will continue this for a few years. Right? Is that what we hope? So, as an editor, where do you see we can sort of improve this document, or is it sort of perfect as it is?
I think that making connections better is always something that we can push more towards. It's that we're always up against the deadlines, and so to do this well in a perfect world, we'd be able to have a period of time where we have each other's sections, we're not right up against the deadline to submit, or we have more flexibility between the internal and external review to then make more solid connections, have like me as the editor say, oh, you know what, this pattern here relates not just to this, but to, and you know, some authors do better at that than others at linking these things up. But it's all a very coherent picture. And you know, even as I was rereading this stuff and putting it together for this presentation, I was making more connections that, you know, given more time, we could make these better. We could paint a better kind of cohesive picture of what's going on in the ocean. I think that's the lowest hanging fruit that could be really tackled. There's room for additional inputs besides, I think, the things that I showed here. It would be nice to see more. There is typically an MOC chapter, but it would be nice to see more on some surface current changes, and that's not simply related to the overturning circulation. And how those are related to the evolution of some of the changes that we see, for example, in this plot over a very long time period. And I think that I'm really glad to see this emphasis towards longer term trends rather than, I think, as back in time, 5-10 years, there's much more emphasis on the change from one year to the next. And so I'm really glad to see that there is this kind of shift towards understanding these longer term patterns, as well as, you know, the typically El Nino and NAO kind of related changes from one year to the next. Gustavo.
Rick, you included in your section sargassum and red tide, because they are extreme events. Is there a connection between, and you talk about the connections between the different sections, with the other sections with respect to extreme weather, to fisheries, or to...
So Gustavo's question, is there a relationship between the sargassum and red tide?
No. About the oceans with extreme weather or fisheries or any field that could be affected by this.
Okay, gotcha. Yeah, so it's a sort of a variant on Rick's question, which I didn't repeat, and I should. His question was, what could be done to make this chapter better? Gustavo's question, and I really emphasize the connection from one section to another. Gustavo is saying, well, what about to the other chapters of the State of the Climate report? For example, extreme weather events, fisheries and such. That is a higher level of making connections that would absolutely make the overall report better, because there are other chapters that are dealing with changes in fisheries, other chapters related to extreme weather events. And by the time all of this is compiled, there's not a lot of room to go back and really edit the individual chapters to make those trans-chapter connections. That really is the work of the lead editors to make those connections, and I think that's typically done in their introduction chapter, which is the final piece that's written, where they will overview all of the chapters. They do try to make connections between, for example, you know, you have the combination maybe of anomalously high ocean temperatures, but also El Nino wind shear, and then you want to look at hurricane intensity in the tropical Atlantic. You know, those connections are typically made there, as well as in the extreme weather section, but could be enhanced. And that, I think that would be a pretty good way of kind of moving this forward. But again, it's a difficult thing to do in practice when we are trying to write this for the middle of the year based on data through the end of the year before. And yeah, it's a logistical challenge. But yeah, I think you're absolutely right that would be wonderful to see enhanced. Any other questions? Anything online?
Is everything doomsday here?
You know, as you look at, is everything doomsday is the question. I mean, we're scientists and we're performing a huge experiment, not us personally, the society is, and so it's sort of an interesting time to see what happens when you whack a climate system very, very intensely and get to see how the system responds in all sorts of time and space scales. It's not a lot of great news when you look at sea level rise, for example, especially when you live in low-lying areas and you've invested a lot of your personal money in property and such. But it's not all bad news either. We certainly see that changes like surface currents are really much more significant indicators of year-to-year changes, but all of these integrating effects. And another, for example, we don't talk too much about, in this oceans chapter, about changes in oxygen content at depth. But it would be nice to, when you talk about how to make this better, it would be certainly nice to see a chapter on the changes of the oxygen minimum zones. And again, okay, so isn't that kind of gloom and doom? Well, it's an interesting story, and it indicates it's an integrator of longer term climate changes that are less affected by these very, very rapid changes like what dominates the picture of sea surface currents. When you're communicating this to non-scientists, I found nothing shuts down the conversation faster than being all doom and gloom. And so I think it's important to talk about these changes in a matter-of-fact way, to basically counter the bad information that's out there, that things are getting warmer and colder all the time, and so we can't really tell what's going on. Just get that message out, and I think try to avoid the doom and gloom. I think that's just the best way we have of communicating this, and who knows what we as a civilization will do in the future to address this. But there's a lot of things that we could be doing now, and so let's not give in to doom and gloom when we message this.
Yeah, I think you sell it as a challenge.
Sell it as a challenge, absolutely.
It's something that we have to adapt to, and sort of state it, at least what I do, is state it as a matter of fact that our belief is that this is happening, but we can, as humanity, we can deal with it. And we have to deal with it. But it is sort of,
Yeah, the fact that we have done so much to the world kind of shows the power that we have, and we're smart.
You don't have to believe it.
So let's just combine these two. Thanks everybody for your attention. Thanks for coming today. I appreciate it. Yeah. So I do see a comment, let's see, questioning who is the intended audience, and the intended audience is the general scientifically literate readership of BAMS. So BAMS in general is aimed not at oceanographers in particular, but at kind of people who are scientifically literate and interested in what's going on in the scientific realm. So yeah, that's generally who this is written towards, and who we editors are kind of trying to aim this towards as well. There was another question about whale deaths along the Pacific coasts, and I'm afraid I do not know the answer to that. There is another chapter that addresses these biological and fisheries related issues, and hopefully that information is there. But as I mentioned, these chapters are all out for external review, and I have not seen those other chapters yet. So I hope that the answer to your question is in that chapter. Thank you all online for your attention.